Hello everyone and welcome to the session. We are going to take this discussion forward and talk about a few more things. So even before that, we have briefly spoken about the CRISP MLQ methodology, and we have been traversing all the various phases. And we also discussed about splitting your data set into training, validation, and test. Why do we need validation data set? Okay, in what scenarios you will have your data set split into three parts, that is training, validation, and testing. And what are the scenarios where you just need training and testing data sets? Okay, this is what we have spoken about. So we have in the due course discussed about regularization. At least we got introduced to the term called regularization. Then we have discussed about something called as random seed or setting the seed or random state, whatever you want to call that, to ensure that the underlying data always remains the same. Right. And then we have spoken about, something called as information leak, because of which this validation data set comes into picture. We discussed that every algorithm will have bunch of hyperparameters, which are options within every algorithm, which can be changed and you can experiment your results. We have discussed all these things and a few other things, such as what do you mean by overfitting or variance, what do you mean by underfitting or bias, etc. And then this test error is also called as generalization error, because you're building a model and you want your model to generically apply on the future data. So hence it is called as generalization. You want your model to generically apply onto the future data. You don't want it to be very specific. That means only if the future data is very, very similar to your training data, only then should it work. Of course, it should work if your future data is very similar to your training data. But if your future data is slightly different than your data on which you train your model, still your model should work. That is called as generalization. You're making your learning, your model which has learned, generic to the future data. All right, now let's take this discussion forward and talk about a few more things. A lot of interesting things are going to be discussed in this module. Once again, I have this habit of talking about concepts which usually people ask in interviews. That way, I'm going to hit two birds with the same arrow. Right? One is we will learn the concepts. Another thing is we'll also prepare for the interviews. Okay, so hence I request you all to pay attention. And I keep telling to people this, that two things you need to remember. In this module, we are going to look at hands-on when it comes to programming. So let me upfront tell you that any programming, including Python programming, the only way that you're going to learn is by typing. You type the code. If you see that on the learning management system or from somewhere you could get access to some code, then do not just open that and keep running line by line. Don't do that. Doesn't help. For example, say there is this code, import torch. You should not feel that, hey, this is such a simple code, import space torch. So I'll just select that and click on run. If you do that in your lifetime, you will not learn. In your lifetime, you will not learn, friends. You will learn only when you type. So the moment you see this import torch, you need to type it. You open a different window, whatever ID you're using, open a different window of that and start typing this. Only when you type, you'll learn. You'll be tempted, after a few days, you'll be tempted that, this is such a simple thing. There is another code called as import numpy as np. This is such a simple line of code. Do I need to run it always? Yes. Until you get a job in data science. Until you crack your interviews, you need to keep typing. Don't get lazy, please. The moment you get lazy, that, oh, why should I type these things? Let me select and run. I'll eventually learn it. No, in your lifetime, you'll not learn. So the only way to learn programming is by typing each line of code. Whenever you see it, each line of code, please type. Keep typing. In that way, throughout your training, you'll type. For working on assignments, you'll type. For working on the projects, anyways, you need to type. You'll gain that mastery. Okay. All right. This is one very important thing. And the second thing is, do not forget to do your research. Whenever you get a problem, in practical world, when you join companies, there won't be anyone to help you or assist you. The only way out is this. Internet, Google search. Search, access as many URLs as possible, as many websites as possible, and fix the issue. You need to fix it. Don't keep looking out for easy solutions, easy answers. This person is there, they'll help you. Or we have teaching associates, they'll help us. Of course, they will help. But what is your contribution to your own career? You want a job. You want to face interviews. You want to become successful. Why should you always bank on someone else, right? Only after you do all that research, despite that, if you cannot get a solution, then reach out. That's the best way. Okay, these are the two things that I'm going to give you as key takeaways. Okay. So friends, here you have something called as loss or error. Okay. For now, we didn't discuss about loss. We will discuss about loss very soon. So this is a loss. Loss value should always be less. It's like error. Your error should always be less, obviously, right? You want your error to be small always. And that is on y-axis. And then you also have x-axis. Something called as training time is given, but I will change this training time because we are getting into deep learning now. I'll talk about something called as epoch. Okay, what is this epoch? Suddenly you introduce a new term. Just get introduced to the term. We are going to discuss about that in detail. This is one more thing that I do. I introduce you to a concept or not concept. I'll introduce you to certain terms, which I'm going to discuss in the next 15, 20 minutes. So that at least you're familiar with these terms. And then I get into the concepts. So this is my way of teaching. Okay. As and how you keep increasing the number of epochs, your loss will keep on decreasing. It will keep on decreasing. Loss for what? On your training data. We know that once we have data, we will split that data into training and test. And then you build your model on the training data. And then you test it on the test data. Simple. And then you also need to test your model on the training data. So you get test error, training error, or test accuracy, training accuracy. So when you keep on increasing the number of epochs, what is an epoch will get the data. Your loss or error will keep on decreasing. But then when you test that model on the test data, your test loss or error pertaining to your test data will reduce until certain point and then it will start increasing. So we as data scientists or AI experts should stop at a specific point where the divergence starts. So your test loss is increasing, your training loss is decreasing. There's a divergence. Okay. Test or validation, whatever you want to call, right? If you also have validation data, then it's called as validation loss. Okay, we already discussed in the previous module thoroughly about that. Okay. So you have the training error or loss, which is reducing. Loss and error are not the same. We'll discuss about that later. And then the test or validation error or loss is increasing. Wherever it diverges, see the divergence is increasing here. If you observe this, it's getting diverged. So that is a point where you stop and you say that, okay, if I run these many epochs, whatever be 1, 2, 3, 4, 5, 6, in that way, we have all the epochs. At fifth epoch, maybe training and validation or training and test loss are the same, more or less the same. There's no huge difference. You stop there and say that beyond 5 epochs, if I train my model for 6 or 7 or 8 or 9, what is happening to your model? It is overfitting. So this point where your training and validation or training and test error is the same, almost the same. This is called as right fit. So if you stop with fifth epoch, it will become a right fit model. But if you add more epochs and run your model, it becomes overfitting. So a model is getting trained very well, absolutely. That's why the loss is getting reduced. But then when you test it on the test data, it is increasing. So your model is learning on your test data amazingly well, but the moment new data, that is test data, is introduced, it is confused. Right? So if you increase the number of epochs beyond this point, it is called as overfitting. So all this zone here towards the right of this vertical line is overfitting. But then if you do not train for sufficient number of epochs, if you say stopped at second epoch or third epoch, you did not even train for sufficient number of epochs, then you're not doing justice. You're not hitting the minimum loss or error. So that region is called as underfitting. So if you stop at second or third or fourth epoch, you're under training. It's called as underfitting. You're not training sufficiently. You're underdoing things. You're not using the full potential. Okay. Overfitting is called as variance, as we have spoken yesterday, and underfitting is called as bias, just in case you're interested. The same thing is explained using this and that. So here, before training, the model starts with a random state. What happens is in neural network, there will be something called as weights which are randomly initialized. Just remember that. We'll get into thorough depth of it. So all the black circles are one class. All the other gray circles are of different class. So you have a two-class problem. So when the weights are randomly initialized, your classifier is not going to segregate them properly. All the blacks should be on one side, all the gray circles should be on another side. It's not segregating correctly. And then beginning of training, the model gradually moves towards a better fit. That means as in how it keeps training the model, it will start adjusting this classifier slowly and steadily. And when you further start training it, it does a good fit. And then finally, but then, if you continue training it again and again and again and again for far too many epochs, what is happening here? You run into a stage of overfitting. Look at this, what it is doing. It's exactly, classifying in such a way that all the points which are towards the right of this curve, dotted curve, are black circles. And all the points towards the left of this dotted line are gray circles. Okay, but this scenario is called as overfitting. Should not train beyond a point. I mean, it's like by-hearting the question and answers. The moment there is a slight change in the future data, your model doesn't work. So that's one thing that we need to bear in mind. Okay. Then you test on the test data. Here, during the test time, your model is fitting very well on the test data. Everything towards the right of this dotted line belongs to our filled circles are black circles, and all the data points towards the left are gray circles. And then performance of okay. If you have a model which is overfitting, then it won't work like this. It will work like this. Overfitted model. Right? Because it tries to do that overfitting. Look at this dotted line here. It's trying to do the same thing. So it doesn't really work well on the test data if your model overfits. But if you have just about a right fit model, then it works well on the future data also. Just bear that. Same thing is explained here. You will have regression or prediction problems and classification problems. Here, this curve is actual data. This red line is the fitted line. Regression, right? If you remember that. So here you have polynomial curve. The curve, actual data, follows polynomial pattern, polynomial distribution. And it is polynomial with 2 bends, means 3 degrees. Polynomial with 3 degrees. But you didn't consider that. You just built a linear model. This is how it will try to fit. This red one is the fitted line or the prediction line. If you probably, this is a polynomial with 3 degrees, right? So in your model, if you have output variable and input variable, and if your actual data, when you plot it, if it follows this distribution, then in your model, you need to include x, x square, and x cube. You need to add 2 additional variables, x square and x cube. Why? Because it is polynomial with 3 degrees. Since you have 2 bends, 1 bend here, 1 bend there. If you have 2 bends, 3 degrees. If you have 3 bends, 4 degrees. If you have 4 bends, 5 degrees. If you have n bends, then you'll have n plus 1 degrees. Since you have 1 bend here, 1 bend here, 2 bends, you'll have 2 plus 1, 3 degrees. Three degrees means x, x square, x cube. That would help you come up with a right fit model. This is a right fit. However, if you increase the number of degrees, if you say, let me add x raised to the power 4, x raised to the power 5, x raised to the power 6, x raised to the power 7, x raised to the power 8, x raised to the power 9. If you keep on increasing, this is what happens. The green line is your actual data, and the red line that you're seeing is your predicted. So you're overfitting, you're overdoing. So this scenario is overfit. And this scenario that you're seeing here is underfit. You should have ideally added x square and x cube, polynomial with 3 degrees. That is what you should have run actually. But you're running a linear regression, so it doesn't work well. On the other side, you are adding more inputs. That is, you're adding more transformed inputs. That's just overfitting. In classification also, if you're underfitting, this is how it will be: the red cross and the blue circles. Right fit is this. This is overfit scenario. One another thing is, say the original data that you have in your data set, when you try to visualize it, say it follows this kind of a distribution, just for understanding. This kind of a distribution is what it follows. But then if you do sparse sampling, sparse means if you take only a few observations from this data set, from your, say you have population data, means say you have HSBC Bank, which has 14 million customers. So all those 14 million customers database is what you have. The entire database of all the customers of this HSBC Bank would be called as population. It doesn't make sense to analyze the entire population. Be time consuming, okay, and it will be costly as well. It will take huge amount of time. Hence, what we do is we take a sample from this data, maybe 1.4 million, 1 million, whatever. You take a sample. When you take the sample, if you take only 10,000, 20,000 out of 14 million customers, if you take only say 10,000, 20,000, 30,000 kind of data points, that's called as sparse sampling. That means you're not taking sizable sample, you're taking a very small sample. When you do that and when you train your model, since this is your population, from that randomly you're taking only these points. 1, 2, 3, 4, 5. Only a few points you have taken. Then if you fit your model will fit like this. It will try to capture the patterns of those data points like that. But your original data set is following a different distribution altogether. How do I fix this? So if you take less sample, it doesn't give you a good model at all. It doesn't capture the patterns well. On the other side, if you have dense sampling, meaning 14 million customers we have in our population. Let me take maybe 1 million customers. So you're taking slightly bigger sample. When you take bigger sample, chances are high that you might choose your sampling technique might choose all these data points from your data. Then when you train your model, it tries to capture the patterns. It tries to capture the pattern. And that's the exact pattern in your population as well. So samples should always be representative of your population. Means whatever your population has, whatever distribution your population has, that has to be captured by samples. So please ensure that whenever you work on your projects, you have sizable data to work with. Okay, next. How much data should I take into training and how much data should I take into validation? Friends, there is one industry standard. When you have thousands of data points, 10,000, 20,000, 30,000, 40,000, in that way, in your training data, you can have 60%, 20% in your validation and 20% in your test. If you have only training and test, then have 60% in your training data. And then 20% in your, sorry, 80% in your training data, and then 20% in your test data. This is the standard. But you can take 90% training, 10% test, 95% training, 5% test. It's up to you. The more data you have in training, more patterns your model will learn, because you have more observations to be learned. If you have more data in test, you can be more confident about the test accuracy. Obviously, right? When you're doing testing on a lot of samples, a lot of examples, a lot of observations, a lot of test data, then you can be more confident. However, if you have really large data set, millions of records, then you can have 98% in training, 1% in validation, 1% in test. If you really have huge amount of data, this is what you can do. 98, 1. Okay. Next. Different algorithms behave differently, friends. If you have, or if you keep increasing the sample size, If you look at this dotted line belongs to an algorithm called as logistic regression. What is happening is accuracy increased up to a certain point, and then accuracy became constant, stable. So increasing the sample points beyond 1,000 will not make any sense when it comes to logistic regression. One more reason is that within logistic regression, you'll have less hyperparameters. There are not many hyperparameters to play around with. So if you don't have many hyperparameters to play around with, even if you have a small data set, good enough. But then when you look at decision tree, this solid line is decision tree algorithm. When you keep on increasing your sample size, the accuracy of the model keeps on increasing. It really depends, right? So that is, I mean, one more classic reason behind this is because decision tree has more hyperparameters. Okay. So you take a judicious call. Next. If the output variable is continuous, say you want to predict the salaries of people, interest amount, loan amount, so on and so forth, output variable will be called as continuous. When you have continuous output variable, there are certain error measures such as mean error, mean absolute deviation, mean squared error, root mean squared error, mean percentage error, mean absolute percentage error. In this way, there are a lot of error functions. Okay, and here assume that you are forecasting the number of products, the number of television sets, number of TVs that you're selling. For the first month, say, let me call this as month of Jan, Feb, March, April. Say you have 4 months. Month 1, say you sold 100, but when you have forecasted using a model, using model 1, it was saying that you would actually sell 101 television sets. Actually, you sold 100. So predicted value minus actual value. Predicted value minus actual value will give you error. Predicted value minus actual value will actually give you error. So you got an error of 1. For the month of Feb, your model predicted that you will sell 199 television sets, but you actually sold 200. So predicted minus actual is error, minus 1 you get. 199 minus 200. For the month of March, you're saying that you sold 301 television sets, but actually you sold 300. When you subtract 301 minus 300, you get 1. In the month of April, you sold 399 television sets, but actually, your model is predicting that you're going to sell 399 television sets, but actually you sold 400. Predicted minus actual will give you error, which is minus 1. Okay, you got that. And you also used a different model. You tried different technique. And that different technique is giving 110. It's telling that you will sell 110 television sets in the month of Jan, but actually you sold only 100. So predicted value minus actual value will give you what? Error. Okay. For the month of Feb, your model is saying you will sell 190 television sets, but you actually sold 200. When you subtract, you get minus. For the month of March, 310 is what your model is predicting, but actual is 300. When you subtract, you get 10. For the month of April, your model is saying 390 television sets is what you're going to sell, but actually you sold 400. So 390 minus 400 is minus 10, right? So these are the various values that are calculated by both the models. If you take mean error, just take an average of all these things. If you take average of all these things, that means add everything, divide by the total count. When you do that, 1 minus 1 plus 1 minus 1, you get 0. 0 divided by 4 is 0. So mean error will be 0 for this model. Here, 10 minus 10 plus 10 minus 10, when you do that, you get 0. So when you look at mean error, both model 1 and model 2, you feel that are equally good. Without looking at the underlying data, if you just look at the mean error, it says that both the models are equally good, which is not the fact because of this negative values. So people came up with something called as mean absolute deviation. If you take absolute value of this, you get 1. Absolute value will make your negative value become positive. Then if you calculate the mean of this, you get 1. 1 plus 1 plus 1 plus 1, right? 4 by 4 is 1. And here, if you take modulus of all of these, you get 10, 10, 10, and 10. And then when you take a mean of that, you get 10. You add all these numbers, divide by 4, because you have 4 numbers. You can also square. Okay, you can also square your errors, and that will also remove the negative sign. Friends, why do people prefer square than modulus? Right? There is a reason. In certain algorithms, you'll have calculus derivatives, which comes into picture. Derivatives won't work when you have modulus. Right? It will work well when you have square. Okay, when you have modulus, it doesn't work, but when you have square, it works well. That is the reason why usually square is preferred. So when you square all these numbers, you get 1. And then your mean square error will be 1 here. For this, when you square all these values, you get 100 everywhere. And when you take an average, you get 100. But the units associated with this will get squared. Suppose this is in dollars. It will become dollar square. Suppose these are in dollars, it becomes dollar square. To get rid of that, you come up with root mean square error. You get $1. When you take a square of this, you get $10. Okay, but then in the industry, we prefer mean percentage error. It's easier, right? That what is your error? You can say it is 10%, 20%. People understand well when you represent something in percentage format. And how do you measure that? Mean percentage error, etc. Take the error divided by the actual value. If I say 10 is what percentage of 100? What will be your answer? 10 out of 100. Say you got 10 marks out of 100. What is your percentage? It will be what percent? 10%. 10 by 100 will give you 10%. Of course, you multiply it with 100 if you want in percentage. In that way, 1 is what percentage of 100? You got error of 1. 1 is what percentage of 100? 1 by 100. Minus 1 is what percentage of 200? Minus 1 by 200. 1 is what percentage of 300? 1 by 300. Minus 1 is what percentage of 400? Minus 1 by 400. This is how much error with respect to the actual. That's what you can do. When you take an average of all these, you get mean percentage error. Same way here also you can calculate. But then suppose here also you had 100, 100 and 100. Then what happens? This will be minus 1 by 100, 1 by 100, minus 1 by 100. Then when you add, you again get 0. 1 by 100, minus 1 by 100, plus 1 by 100, minus 1 by 100. Again you get 0. So to do away with this negative sign, again you take absolute value. And take an average of this, and you get mean absolute percentage error. Or people pronounce this as MAPE value. And there are a lot of other things. The reason why I'm talking about these is because these are called as what? Error values. These are called as error values. And if you get an error of say 3%, that means accuracy will be 97%. When you add these two, you get 100%. But error can also be represented as a raw data. It can be 0.3 or 0.03. And in that case, accuracy would be 0.97. When you add these two, you get 1. Either represent your error and accuracy in percentage sense or use it as a regular value. Okay. So let me take this question from Monali. Yeah, Monali, please can you unmute yourself?
Yeah, hello sir, good afternoon.
Hey, good afternoon.
My question is like when we have a small data set, say like 1,000 records or something, so which approach we should follow, like for oversampling or undersampling, or we should only go for the same number of records from that data set? Because I tried oversampling, undersampling, it's not improving the accuracy. So which will be the better approach in taking the same number? Yeah.
When do we use oversampling or undersampling?
When we have imbalanced data.
Imbalanced data set, right?
Yes.
So you're talking about imbalanced
data. Yes. Yeah. Yes.
When you have imbalanced data set, how do I deal with it? Is that your question?
Yes. How to deal with it in case of less number of records?
Yeah, less number of records or more records. You have all these various techniques which exist. Okay, you can try out all of these things. Which technique exactly works? No one can tell you. Right? But then you can try out k-fold cross-validation, which is one thing which people use when you have less amount of data. But my best bet would be you please experiment with all these options which you have, and then figure out one technique which gives you the best answer. All right, Monali, hope you're getting it. In interviews also, when people ask, this is the answer that you need to give. See, just by looking at the data, we cannot decide on which technique works well, but we can try out all the various techniques and figure out which technique is helping us give better accuracy. Otherwise, you can say, to be on safe side, I use k-fold cross-validation as a sampling technique to split the data into training and test, right? You use k-fold cross-validation when you have limited amount of data. And also it is imbalanced. When you have both these things coming into picture, this is how you handle. So next. Yeah. This is about output variable being continuous. This is error that we are talking about. There's something called as loss and cost. We'll get there very soon. I think in the next few slides, we need to get there and talk about deep learning, and that is when we'll talk about optimization techniques and all that. Okay. So when your output variable is discrete, categorical, in two categories or multiple categories, doesn't matter, we end up using something called as confusion matrix or cross table or contingency table. All mean the same. So if you look at this, you'll have positive class and negative class, like what we have spoken yesterday about earthquake. If you're going to have earthquake, it's a positive thing. Positive in the sense, positive case in the data, okay? COVID positive is not good, right? But it's called as positive. You're tested positive. Earthquake positive means there will be earthquake. Negative means there won't be earthquake. If you're predicting that there will be earthquake, it's a positive case. And if it is correct, that's a true alarm. True means correct. If you're predicting that there won't be earthquake, and in reality there was no earthquake, then it's a true negative case. You have correctly predicted that there won't be earthquake. If you're predicting that there will be earthquake, but in reality there was no earthquake, then it's a false alarm. You're incorrectly telling that there will be earthquake. False positive. If you predict that there won't be earthquake, but actually there was earthquake, actual class is positive, then this is also false alarm. False negative. Okay, meaning you have incorrectly predicted that there won't be earthquake. This is how confusion matrix will come into picture. Is false positive bad or false negative bad, or are both of these bad? It depends on the business problem that you're solving. But in this scenario, false negative is more dangerous. Right? Correct. Because you're saying there won't be earthquake, but in reality there is earthquake, loss of life, property, you don't have any business continuity plan, you need to then remove the debris, and then a lot of people might be stuck underneath, who knows, they might be alive. So too many things come into picture. Okay. By looking at this confusion matrix, if you want to calculate accuracy, you just look at how many times did I correctly predict, or how many times did my model correctly predict. True, true positive, true negative. Out of, divided by out of overall predictions. You take all the predictions. Out of all the predictions, that is true positive, false negative, true negative, out of all those, how many times did my model correctly predict? It's true positive and true negative. That would give you accuracy. And if you want error from this, you just say 1 minus accuracy will give you error. Or you say 100%, if you're calculating in percentage terms, 100% minus accuracy percentage will give you something called as error percentage. That's how it works. Okay, next. Even if you have, instead of two categories or two classes, if you have more than two categories, that is multiple categories or multiple classes, it doesn't matter. Same confusion matrix, you just extend it. For example, say you have a video. Okay. From that video, say you want to predict whether a person is bending or performing an activity which is jacking, jumping, running, p-jump, side, skip, walk. So you have all these classes. Instead of two positive, negative, you have multiple classes. So what? Along the diagonal, always you'll have the correct prediction count along the diagonal. Here also along this diagonal, you have true predictions. Here also along the diagonal, you have true predictions, meaning 100 out of 100 bend class. Someone is bending in the video. Your model also predicted that that person was bending. But then if you look at running, okay, only 89 cases, your model classified that someone was actually running, and your model also is predicting that person is running. Remaining 11 out of 100, remaining 11, your model is classifying. Actually, this guy was running. I mean, these people were running. These 11 people were running. Actual class is running, but it is showing us they are skipping. Actually running, but it's showing us they are skipping. So you add all those diagonal elements, divide by the overall count, it will give you accuracy. And this earthquake yesterday we discussed about what is the cost of a false alarm, false positive alarm, what is the cost, false negative alarm, what is the cost, total detection cost. I mean, if you go wrong, incorrectly, if you classify either positive or negative case, what is the overall cost? This is how you calculate. Right? So number of false positive, number of cases where you have incorrectly classified, multiplied by the cost associated with that, plus number of false negative, number of cases where you have false negative, multiplied by the cost pertaining to it. You have to just, excuse me a bit. Okay, sorry about that, friends. So I had to take the call. Sometimes calls continuously keep buzzing me. Okay. Then, so that's how you calculate the cost. Let's move on. What's the time, by the way? Yeah, we still have time. Okay. So you first define the goal as part of your any project, machine learning. Deep learning is a subset of machine learning, right? Within machine learning, you'll have a lot of algorithms. You'll also have deep learning algorithms. You define the goal, whatever you want to achieve. Say you want to reduce the number of people who resign from the company by 5%. Maybe that's your goal. To solve that purpose or to achieve that goal, you bear that goal in mind. And to achieve that goal, you go and collect the data. Whatever data you're going to collect should be something which will help you achieve your goal. How do you achieve that? See, one thing is do a simple Google search to understand what are the models that were built to predict people resigning or retreating. You get bunch of documents, read those, gain some good understanding. What data people have used to solve those business problems. Make a note of all those variables. Go collect the data for that. That solves your problem, right? To a great extent. And then you can become as creative as you want once you get more understanding about the kind of data which people have used in the past. You get better understanding. Please do not assume that the project that you're working on always will be novel project. Novel means very new. For the very first time people are doing on the planet. Very rarely something of that can happen. So just do research that solves majority of the problem. Okay, so you do the data collection based on that. Then you perform exploratory data analysis. Usually when you perform exploratory data analysis and visualize, BI tools are preferred. Business intelligence tools such as Tableau, Power BI, ClickSense, etc. Then of course you can use Python. No one is going to stop you. It also has good visualization, but not as powerful as Tableau, Power BI, Click, etc. You use any of those, draw a lot of meaningful insights, complete your descriptive analytics, and do the presentation to the client. Most often than not, your customers will love to look at the insights that you draw from your exploratory data analysis as part of your descriptive statistics or descriptive analytics. The insights that you glean, the insights that you bring out would be more meaningful for your customers. Trust me on that. They'll love you for that because these are all going to unearth a lot of interesting things which can be acted upon immediately. Then once you do this exploratory data analysis, right, of course you get a lot of insights, but you also get insights on what kind of pre-processing is needed, what kind of data cleansing is needed. And this is also called as data munging, data scrubbing, and there are multiple other names which are given to this. Then you partition your data into training, validation, and test. You partition the data. And after you partition the data, you apply a lot of machine learning techniques on your training data set. Then you test on your validation data or your test data. And then you compare all the different models and figure out which model is giving you the least error or high accuracy, whatever you use, error or accuracy. Error should be low, accuracy should be high. And then once you figure out what is the best model, go deploy it, deploy a model in production. But then you also need to continuously monitor and monitor your model constantly. Once deployed doesn't mean it will work for the rest of the life, right? You'll have certain issues, challenges, okay? And now let us get into deep learning history and applications of that. Way back in 2012, see, neural network has been there for ages, right? For decades it was there. But people were not taking it seriously. Why were people not taking it seriously? Because they didn't really see the result, right? For running your neural network algorithms, two things. You need huge amount of data and you need very high compute. Okay? For running your neural network algorithms, two things are needed. One is you need huge data and you need very high compute. These are two things which would be needed. And until 2012, a lot of people were using traditional machine learning algorithms, not deep learning models, They were using traditional models, and traditional models were giving very good result, and the results were equivalent to deep learning. If traditional models and deep learning models are going to give me the same result, why will I go with deep learning? Because deep learning will need high compute, I mean high RAM. Your memory should be like 32, 64 GB, 128 GB, high memory. You should have very good processing processors, right, to process the data. So the hardware that was needed was very, very expensive. So people were not actively, pursuing neural network in research area. But in 2012, there was a guy by name Alex Krzyzewski. Alex Krzyzewski. This guy was working in University of Toronto, Canada, right? And then he and his team have competed in a competition which was called as ImageNet competition. ImageNet competition is a competition which was performed previously on images. So this specific thing was part of a competition called as Wikipedia is not for profit, right? So they collect money like this to maintain it. Anyways, that's just charity that they're asking. It's up to you. If you look at this, this was a competition. ImageNet Large Scale Visual Recognition Challenge. They started this in 2010. Okay, and the objective was take the images and automatically your algorithm has to give a name to that image. It has to automatically give a name to that image. It was image detection that you had to actually do. So here in the actual ImageNet project, there were 14 million images and there were 20,000 categories. 20,000 categories. Means balloon, strawberry, panda, car, bird, many things were there, right? 20,000 categories were there. But for this competition, they didn't give all 14 million images. For this competition, they have given only 1.4 million images. And they told, okay, use machine learning algorithms. Either use traditional or deep learning, it's up to you. Use machine learning algorithms and solve this problem, and they have given only 1,000 categories of images, like cat, dog, right, and balloon, strawberries, things of that kind, 1,000 categories. And whoever gives the highest accuracy will win the competition. So it started in 2010. Just remember that it started in 2010, 2011. The people who have won the competition were the people who have, I think they haven't given. Now they stopped the competition because accuracy levels now, in 2017, ImageNet stated it will roll out a new thing because in 2017, in this ImageNet competition, 29 of 38 teams got an accuracy of more than 95%, more than human accuracy. What is the goal of artificial intelligence? Goal of artificial intelligence is to achieve human accuracy, human intelligence. If you can automate it, it's called as artificial intelligence. So if you can achieve an accuracy of more than what humans typically do, then that project is considered to be job done. Doesn't make sense to keep investing more time effort on that. Anyways, so 95% was accuracy. Then now I think they rolled out something called as 3D objects. all the images that you have are two-dimensional, right? Whatever, I mean, you're looking at me, I'm two-dimensional for you. Whatever you're seeing on the screen is two-dimensional because screen has, your width, length. So it's two-dimensional. All right. So in this specific competition, in 2017, they stopped. They told enough, we achieved human accuracy. But in 2012, there was some revolution which happened. And there was a team which has manually extracted the features from the images and they have run traditional machine learning algorithms. I think SVM, if I'm not mistaken, support vector machine was used. I mean, that gave an accuracy of around, some 95, 73, 74% accuracy. In the same year, Alex Krzyzewski and his team, they have used neural networks. They've used convolutional neural networks. And they achieved an accuracy which was much higher, approximately 10% more accurate than the traditional machine learning algorithms. And everyone was like, wow, what is this neural network? Something it has done. It has given an accuracy of more than 10% in comparison to traditional machine learning models. And they were like, okay, let's see what these people have done. Entire world started looking at neural networks. It was there since long, but 2012 was a revolution. Alex Krzyzewski, when he became a big chap now, because of that 2012 only. Since then, people started very actively using neural network and very actively pursuing that. And the kind of results it is giving is mind-boggling. However, it is a black box technique, meaning you cannot explain the model. Like if you have a decision tree, it will have all the branches. Like this guy is a student, next branches, this guy has a credit score which is high, next his education is graduation, this person will buy your computer. So it's a branch, neat explainability will be there in decision tree. With regression techniques also you'll have explainability. A few people prefer explainable models, especially when you have regulatory bodies to whom you need to explain. If it's in finance or banking, why did you reject the loan? If it's in healthcare, why are you saying this person has cancer? That explainability they are expecting. But your neural network algorithms doesn't have this explainability. However, DARPA, US, Wikipedia, Defense Advanced Research Projects Agency. Defense Advanced Research Projects Agency, right? This agency, which was formed 64 years ago, is now working on explainable AI. You know what? They are good 10 to 15 years ahead of the race. We are talking about driverless car and all that now, right? But DARPA has started working on this driverless car, drones and all that in, I think, 2002. 2002, they already thought about this. They're very, very futuristic, friends. Very futuristic. Let me see if I can pull up something for you guys to help understand on how futuristic they are. Yeah, look at this. Unmanned aerial vehicles. When did they start? 2002, 2003 time frame. That was a time when they have actually started off these things, working on these things. Anything that they put their hands on, you can be rest assured that results will be positive. Until now, they're I mean, they have a lot of perseverance. They do not leave it just like that. They pursue it until they crack it. So they're working on the explainability. So probably we'll get more insights as we proceed further. It's a very active field when it comes to research, working on explainability aspects of deep learning. Okay, since then, since Alex Krzyzewski 2012, since then, people have been using only deep learning models, and the models that won the first place on ImageNet competition since 2012 have always been deep learning models, 2013, 14, 15 throughout. This was the architecture that they have used. We'll talk about this. We'll understand it in a very thorough detail. So the previous year, error was 25%. Once Alex Krzyzewski's team came into picture, error reduced to 15%. That is where 10% improvement was a huge improvement. 2010 to 2011 to 2012, when people used traditional machine learning models, improvement was only 1%, 0.5% in that. But they work for entire 1 year and bring about an improvement of 1% or 0.5%. Suddenly, neural network has given an improvement of 10%. People were like, oh, what is this algorithm? Magic or what? Right? So that is when they started observing the skin. These are all the various methods, okay, and accuracies. Human performance is 3 to 5% error rate. When you look at an image and if you're asked to name it, 3 to 5% of times humans go wrong, talking about average human. But then now the models that are being built are giving you less than this error rate. So it's a solved problem. Object classification, image classification is a solved problem. Okay. Since then, deep learning has been used in speech, Microsoft Cortana, Apple Siri, Google Hello. All these are using deep learning models for speech. Then Google has acquired something called as DeepMind. I think recently they came up with an algorithm. Boot, DeepMind boot something. Or yeah, Boot. Right, what this Boot is doing is, I think it is working on some 160 tasks, with great accuracy. Humans, you do many things, right? While you drive a car, you talk over phone, you observe the things, right? You do various things. So, but artificial intelligence, when AI systems are built, it will work on only one thing. Right? So if you are automating a car, you need one model to control the steering. Should I move the steering by 10 degrees towards left or 10 degrees towards right? Or 5 degrees towards left or 5 degrees towards right? You need one model to do that. You need one model for applying brakes. You need one model for looking at images and detecting what images are there. So you need different models in that way. But human, there's only one model, your brain, and that does many things. So that's what is the goal of DeepMind, seems like. And they're trying to do something which will ensure that the model does multiple things, like what human does. If that happens, robots will be roaming on the road, like what we have seen in movies, some scientific fiction movies. You will see robots roaming on the road. If that happens, I mean, it's a very distant dream. At least in our lifetime, we won't see that. Don't worry too much. But given the kind of pace at which AI is growing, even today, in a lifetime, we'll not be able to see. I'm combining everyone who's attending the training. What will we not see? Robots behaving like humans will not be able to see. Okay. So given that, I mean, Atari breakout, I've shown you a video. Brick breaker is what people call it. you will have a slider like this. A ball will keep hitting the bricks and be breaking those bricks. You need to move it, ensure that ball doesn't fall down. That's Atari Breakout. And I played this Atari Breakout on computer in I think 1991, right at my school. I still remember that playing that game. Only for that we used to go. We used to control the keys using the keyboard keys, arrows. And yeah, DeepMind was acquired by Google later on, and it has. There is a game called as Stockfish. Stockfish is a computer chess game. I mean, defeating Stockfish is next to impossible, guys. It's a computer game that I'm talking about, next to impossible, right? It's very, very difficult to defeat that. And this AlphaZero, which is a deep learning model, has defeated Stockfish 28 times in 100 games. Rest all it was draw. So AI is far superior than your powerful computer programs. It can be used in games. And then you can use AI for image captioning. Deep learning models can be used for image captioning. Like two pizzas are sitting on the top of the oven. Detecting this itself is a difficult task. Detecting and then giving a caption to it. Right? That is what is happening as we speak. A group of people are shopping at the outdoor. By looking at this image, it gives us caption. You can use deep learning models for interactive chatbots. If you supply this image and if you ask questions, for example, your chatbot is saying that a man and a woman are holding umbrellas. But if you ask a question, what color is his umbrella? His means it has to go detect who is a male, and then it has to look at the umbrella that they're carrying, look at the color and give you the response. This is a project which was done by IIT Hyderabad folks. Since I'm from IIT Hyderabad, I just put that there. What about hers? Now it has to remember that in the previous question you asked, what color is his umbrella? This question it has to remember, your chatbot. And when you say, what about hers? It has to locate who is a woman in the picture. Do you have women or do you have woman, single or many people? And then you need to look at what kind of umbrella that person is carrying and figure out what is the color and then respond. All these things have to happen in split second. You type it, immediately you get the response. Split second. And these are the kind of models which are solved using AI. How many other people are there in the image? I think 3. There is occlusion. Occluded. They are occluded in the sense one is standing behind another. This leg, if you are able to observe, one person is standing behind. So it is also able to identify that, and it's saying they are occluded one on top of another. On the image, you are not able to see properly. That's called as occlusion. And then your chatbot will go on with that questions. And recurrent neural network or LSTM or GRU or these variants, and now you have transformers, GPT models and all that. People are expecting these kind of things in interviews, and if you can answer these, you get very high salaries. Doesn't mean if you don't answer, you won't get. These are all exceptional things which people are expecting. If you know, be rest assured that you can ask more salary. Okay. And for example, you take all the super hit movies. Netflix also does this. You take all the super hit movies, and that becomes your data set. Train your model on that and tell your model that I want you to generate a new movie script based on the learnings. Take all Rajamouli movies, Bahubali, RRR, and all the other movies that he has directed in the past. Take all the movie scripts, get your model trained on that and say, hey, I want new script to be generated. It will generate one for you. Right? So these are a few things that we learn as part of our AI training. Right? professional certificate program in data science, and in that you learn about all these things. So here there is a speech of Obama, the then US President Barack Obama. He delivered a lot of speeches, and all his speeches were taken. Model was trained, and then you ask RNN model, which is a deep learning model, to generate text, and it generated this text, which is, I mean, you can read, "Good afternoon, God bless you. United States will step up to the cost of a new challenge," so on and so forth. Right? Deep colorization is also something that can be done. You take your black and white images, your parents' marriage photos maybe, and it's been black and white. If you supply that, your deep learning model will automatically put a color, and the color will be very, very similar to the color images. It will look very natural. Right? That's the example. Those are the examples here. If you look at this dog or this cock, right, it's appearing exactly like what it has to. And deep learning is everywhere. It can be used for image classification, speech recognition, language translation, language processing, sentiment analysis, you name it. Video captioning, video search, face detection, and all that. It's there everywhere, friends. And we, as part of 360 Digit MG, have come up with 56 domain analytic programs. And in each of these 56 domain analytics programs, we are now incorporating use cases pertaining to images, videos, audio, and text. Okay. And it's not going to be an easy task. By no means it's an easy task. It's a Herculean task which we have taken upon ourselves, but we will accomplish it. We will do it. 8 months roadmap is what we have laid down to accomplish this. We will accomplish. Okay. And all the different use cases are listed down here. Whenever you find time, you can go explore that. All right. So we need to now enter into the deep learning primer, right? But before we get into deep learning primer, let's let us now proceed further with deep learning primer. These are all the agenda items that we are going to discuss as part of this. So we have, say, biological system, human brain. Okay, and people thought human brain is so powerful. There are a lot of neurons, there are a lot of foldings in your brain, in our brains. And because of that, we can process a lot of data. Then people thought, if we can come up with an artificial algorithm, artificial system, which is similar to human brain, then it is going to work very similar to the human brain. Human brain is considered to be very powerful. It can do a lot of processing. It can store the data right from our childhood days until now. Right, a lot of things it can store. So if you can build a system similar to that, it will work like human brain. That was the idea, and people started off with artificial neural network. So here in human brain, the basic unit of processing is called as neuron. What does neuron do? It processes. If you look at an image, it will process and tell you that that's a bird, that's a tree, there's a computer in that. And typically humans will have 10 raised to the power 11 neurons. Those many neurons will be there in the human brain. And typically 1,000 to 10,000 connections will be there for every neuron. So you have 10 raised to the power 11 neurons, and every neuron will be connected to 1,000 to 10,000 other neurons. And the communication speed is much slow, not slower. I should say the communication speed is much less. That means very fast you can communicate. And the communication is to the order of a few milliseconds. Is of the order of a few milliseconds, basically. Within a few milliseconds, you can communicate. Even if you have a very complex perpetual task, perpetual means something that you do on an ongoing basis. However complicated it might be, if you do it again and again, then you will take less than 100 milliseconds to process that. Also, one more thing is 100-step rule. That means any perpetual task might not pass more than 100 neurons. That means how many neurons do you have? 10 raised to the power 11 neurons. If there is any repetitive task, it will not use more than 100 neurons. Today, since you are listening to all these concepts for the first time, deep learning and all that, you might feel that it is difficult. That's what happens. But if you continuously keep watching the video, if you continuously keep practicing, then you will not use more than 100 neurons. That's a 100-step rule. However difficult it might be, if you do it again and again, eventually it will not use more than 100 neurons. Please bear that in mind, friends. That is important for us, right? Python programming, oh my God, it is so difficult. Of course. Even when you were in school, alphabets were difficult. Tables were difficult. Words and meanings, remembering those was difficult. For that age, that was difficult. But how did you overcome that? By practicing, by doing it again and again. Same thing you do now also. Nothing has changed. You are listening to all these things for the first time. You might be looking at Python programming for the first time. Obviously, we all will find it difficult, but how do we overcome that? Through practice. Do that, you'll not use more than 100 neurons. You have 10 raised to the power 11 neurons in your brain, friends. What will you do with that? Would you underutilize the potential? Not needed, right? Practice. Okay. So there is one more extremely important thing in neural network that is called as compositionality. What does that mean? In neural network, you'll have something called as layers. Input layer. Then you'll have something called as hidden layers. They all might be of same size, or it might decrease and then increase, whatever. And then you'll have output layer. Output layer. These are called as intermediary layers. Intermediate layers or hidden layers. Hidden layers or intermediate layers. Okay. And in every layer, you'll have something called as neurons. Like what you have in your human brain, that way you'll have something called as neurons. Right? You can have as many neurons as possible in your intermediary layer or hidden layers. It's up to you on how many neurons you want to have. If you have more neurons, what will happen? If suppose a human brain has more neurons, they can absorb the concepts very easily. That's called as IQ, intellectual quotient, right? IQ level. This guy's IQ level is very high. This guy's IQ level is not so high. We keep comparing, right, people? Someone, the moment they listen to concepts, they remember immediately. But for a few other people, they have to do it again and again, read it again and again. It is directly proportional to the number of neurons. If a person is having more neurons and utilizing those neurons, their IQ level will be high. And a person who has high neurons, if they are not utilizing, IQ level will be low. But 10 raised to the power 11 is average human has so many. Oh, we have far too many neurons. Okay. And there is something called as compositionality. What does that mean? Human brain typically first recognizes pixels. If you look at an image, say this is a water bottle. Okay, the moment you look at it, first what happens is human brain would look at pixels. Then it will look at edges. Edges, all these edge. This is an edge. Right? This is an edge. Bottle has an edge. Right? These are all edges. Edges. And then if you look at texton, there's something called as texton, the texture basically. Right? Motif is some other component of this. Then it looks at the bottle part, meaning you have a cap, you have water in it, and this is a body of the water bottle in that way. And then the complete object. And all this happens in a matter of a split second, under a millisecond maybe. So that is why you cannot, as a human, differentiate that, okay, my brain is working in this way. I mean, maybe we do not realize that, but researchers who have researched on human brain have already done it. Okay, so this is how your human brain works. When it comes to textual data, first it looks at characters, A, B, C, D characters, then words, group of words, clause, sentence, and then the entire story. Clause means two sentences separated by a comma or a semicolon or a colon. Even for speech, it looks at samples, spectral band, sound, phone, phony, word, so on and so forth. The point that I'm trying to drive is the first, I mean, this is how human brain works. So the neural network also behaves in a similar fashion. The first set of hidden layers capture something called as pixel values. The second set of hidden layers capture maybe the body parts, eye, nose, mouth, ear, etc. Then the next or the final hidden layer will capture the actual face. So it will start from low level details. Your neural network starts from capturing low level details, and it will go on to capture the high level details like human face. So this actually increases something called as representation power. Representation power means the way you learn something, it increases. If you first focus on basics, then slowly increase the difficulty level. That's how typically your human brain works. Okay. This is same compositionality explained using this. So first you, within the brackets, whatever you have, you first explore that, understand that. Then go to the next bracket, then go to the next bracket, right? First calculate sine cube of x, then calculate exponential of this, then calculate cos of this, then log of this. I mean, this is just a math representation to help you understand how that, how your deep learning model first understands the smaller part, then increases the learning capacity. If you take an image as an example, say you have an image, and if you supply your image to your model, deep learning model, the initial set of hidden layers, say you have 3 hidden layers and then one more. So the initial hidden layer captures low level features. Low level features are like edges. Here there is an edge. Maybe here there is an edge. 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 Shadow. Here there is an edge. Maybe it will capture edges, low level details. Next, maybe it captures mid level features. In mid-level features, I mean, low-level features, you have pixel values, pixel intensities, edges, etc. Mid-level features could be some kind of blobs. I'm giving just example, friends. Deep learning is black box. Exactly what feature it extracts, no one knows. Okay, explainability, people are still working on it. Blobs means circles, like you have a circle there, you have a circle there. So something on those lines. I mean, you cannot clearly figure out, but some. And this mesh that you have on the engine in front of the vehicle, probably that is also getting captured in some sense. And next, the high-level features. High-level features are like entire body part, right? Maybe this is a glass door. Maybe this is the engine in that, right? High-level features. And finally, it says that yes, this is the car. So after extracting all the features, it will take all those features. Features are like inputs, right? Features that it has extracted are like inputs. But how did it capture all those features? Automatically. How did it extract the features? Automatically, it has extracted the features. And these features are given to your final model, some classification model, which tells you what this image is. This is called as compositionality. So for example, you have facial images, and you're using these facial images to classify who is there in that particular image. The initial set of, say you're giving your facial images as input to your input layer, which has a number of neurons. Then it gets processed. How and all will get there? High level. Slowly will get introduced to the terms, terminologies, the lingo that is used. Then we will understand at a high level how the algorithm works. Then we'll do a deep dive. So this is a hidden layer, first hidden layer. So it captures what information? Low level information. What hidden layer is this? This is initial hidden. Initial set of hidden layers. They capture what? Initial set of hidden layers capture low level information. Like on a human face, you'll have an edge here, here, right? Here. Wherever that face ends, right, you have edges. Then the next set of hidden layer captures mid-level information. The next set of hidden layers capture mid-level information, such as eye of a person, nose of a person, mouth, ear, in that. It captures body parts. If it is facial recognition. And then you have the final set of hidden layers, which capture the high-level information, such as entire human face is captured, entire human face. And then ultimately, you have the output layer. This output layer will tell you who that person is. If it's facial recognition system, it will tell you who that person is. On the ASPRI learning management system that you see, we have come up with the facial recognition system to log in. You click on login through webcam, it will just scan your face and helps you log in. But we want to avoid the false positives. Right? That means we say that, hey, this guy is Bharani, but ultimately it turns out to be some other person's login, right? We want to avoid that. It's more or less a solved problem, but somewhere when it comes to practical applications, it takes some time. Okay. So this is called as what? Compositionality. Compositionality means slowly and steadily you keep learning in bits and pieces. Okay. So if at all you have to use traditional machine learning algorithms, say you have vision, image. Right? In traditional machine learning algorithms, How do you extract the features? In traditional ML algorithms, how do you extract features? How does feature extraction work? Automatically or manually? We've already discussed this. It happens manually. Manually, you need to extract the features. And these features are then given to your traditional machine learning algorithm for whatever purpose. Could be supervised, unsupervised, task. So when it comes to images, people use something called as shift invariant feature transform, SIFT, or histogram of Gaussians. These are all good techniques to learn. Maybe these all were good techniques before the deep learning era. Okay. Now no one is manually using these, waste of time. But then once you extract the features, either you apply unsupervised learning or supervised learning. Yeah. Do clustering on that or do classification on that. It's up to you. When it comes to speech, manually, if you have to extract the features without giving it to your deep learning models, then you use something called as MFCC, Mel Frequency Cepstral Coefficient. And then you apply your unsupervised learning techniques or supervised learning techniques. Then if you have textual data, natural language processing, textual data, then there is a manual way of extracting the features. You have bag of words, right? You have document term matrix or term document matrix. In that, you populate the data using term frequency or term frequency, inverse document frequency, and a bunch of other things exist. Once you extract parse tree syntactic is another technique to manually extract the features from your textual data. And then you apply your unsupervised learning technique or supervised learning technique. That's up to you. But then if you use deep learning algorithms, do you need to worry about all these techniques? Not at all. Why? Because when it comes to feature extraction, it is done automatically. Okay, automatically you can extract the features. So you have shallow models, which are nothing but traditional machine learning models, wherein you handcraft, manually extract the features, then you supply it to your model. Okay. Feature extraction is manual. Whereas when it comes to deep learning models, automatically features are extracted. How? You have the initial layer, then you have the hidden layers, and then you have the output layer, right? So each of that output layer will give you some features or representations, some features that it learns or representations, both mean the same. Features or representations mean the same. It learns. Here also it learns. Here also it learns. So it will learn throughout. Not towards the end, right? Right from the beginning, it keeps learning. Slowly and steadily it learns. Initially, it will learn the low-level features. Then it learns the mid-level features. Then it learns the high-level features. And ultimately, all that learning is used to do the prediction or whatever is your objective. Okay, now here is where we are going to spend huge amount of time and understand many things. So pay attention. So friends, suppose you have a data set wherein you have an output variable and your say financials. You have an output 1, 2, 3, 4, and 5. And then you have various inputs 1, 2, 3. And say you have 10,000 observations. Okay. If you have 5 inputs in your data set, you'll have 5 neurons in your input layer. This is your input layer. In this input layer, you'll have how many neurons? 5 neurons. But hey, 1, 2, 3, 4, 5. I also see another one. Okay. So what is the equation of line, friends? Y is equal to C plus mx or mx plus C. This is the equation of line. Or a few people call this as y is equal to b plus mx. However you want to write, it's up to you. So if you have a class which has pink crosses and you have blue circles, if you want to segregate these two classes using a classifier, draw a straight line, a linear line, and then anything which falls on the right side is pink cross, anything which falls on the left side would be blue circle. Using a classifier, you're classifying it. Okay. So equation of line came into picture. On similar lines, when you look at linear regression, how was the equation? Y is equal to beta naught plus beta 1. On similar lines, because linear equation, on similar lines, when it comes to neural networks, you will have in this way. If you have more than one input, it will be like this. For linear regression, for neural network, it will be like this. So, now, if you look at this B in the equation of line, or beta naught or B here in neural network, all these three are multiplied by a number 1. If I multiply 1 by B, it will become B. If I multiply 1 with beta naught, it will become beta naught. If I multiply 1 with B here, it will become B. Hence, you add a new input. If you have 5 inputs, you'll have 5 neurons plus one additional thing for this B, which is nothing but this, which is nothing but this beta naught. All these are getting multiplied with 1. So you always say that input will be 1 to this. And then you connect all these things to another neuron. And all these will have weights or these coefficient values or parameters which are randomly assigned. Initially, these weights are randomly assigned. Okay, then suppose this is age, this is gender, say female is 0, assume. Then income is say 10,000. Then say graduation is 1. Okay, in that way you have all these inputs. So you take all those inputs of each row, pass it to your network. When you pass, initially these weights are randomly initialized. Then they get into a neuron, and this neuron has 2 components. One is called as integration component. Every neuron has 2 components, right? 2 components. One is integration component. Another is activation component. So you have one integration component and activation. Here the integration component Usually, integration component integration components vary, but usually the integration component that is used is summation. Summation means what? 1 into b should be b plus w1 into x1 plus w2 into x2 plus w3 into x3 plus w4 into x4 plus w5 into x4. So what are we doing? We are doing a sum product summation. This will give you some number. Say it is giving a number such as 0.8, just for our understanding. So it is giving something called as 0.8. This 0.8 is then given as an input to the activation component. In a neuron, there will be two components, integration and activation. After the integration is done, you take that value and you give it as an input to the activation component. And here, activation functions, like integration function is summation, it can be something else. What else can it be? We will talk. For now, it is summation. Widely used is summation. Almost always you use summation, right? Okay, but there are other things also which can be used, which I'll talk later. And you're taking that and supplying it to the activation component. In this, activation functions can be various things. We'll also talk about that. What did I tell? First, we'll get introduced to terms, terminologies, the commonly used language, lingo. Then what will we do? We will understand the high level overview. Then what will we do? Deep dive. We'll also behave like neural network algorithm, because that's how human brain works, right? So we'll be in sync with human brain so that we internalize things better. All right. So here the activation function is step. It is appearing like a step, right? Climb the stairs. It's appearing like a step. Hence it is called as a step function. This function is called as step function. So here, the way this step function works is, if you have a value which is 0 or more than 0, it will say that output equal to 1. That means if this function, of all these inputs, right, and weights, if this function is greater than or equal to 0, if that value is of xn w, if this function value is greater than or equal to 0, then output will be equivalent to 1. That's how this step function works. If this function value is less than 0, then the output will be 0. You'll have x-axis, you'll have y-axis. If the x value is less than or equal to 0, y will be equivalent to 0. If the x value is greater than or equal to 0, then output will be 1. Why are we using this? Can I not use something else? What is, we'll get there. Just understand the high level thing once again. Okay. In neural network, initially we understand the low level things, small things. Then we move on. Okay. This is how the step function works. Say the output variable here is whether a person will default or not. Default means 1, Not default means 0. That's what is getting predicted. Y equal to 1, y equal to 0. Okay, so that's the function here. This output variable is a function of WT means not transpose, weight matrix, weight vector. Weight vector. Vector is nothing but collection of all these numbers. Okay. So remember one thing, scalar means a single number. Single weight, if you have a single weight, W, it's called as a scalar. Weight could be anything, say 0.8 or 0.01, whatever. Vector means it is represented as this, not transpose. Vector is collection of all these weights like W1, W2, W3, W4, W5. This B is also called as a weight. So all these weights. Collection of all these weights is called as a vector. Then you have matrix. Okay. Matrix, you know how it is represented, right? You can represent in this way also. Okay. Scalar is considered to be zero-dimensional tensor. Something called as tensor. Vector is considered to be one-dimensional tensor. Matrix is considered to be two-dimensional tensor. And then if you have more than 2 dimensions, it is called as tensor. A name. You cannot ask me why are you named as Bharani, or I cannot say, hey, why are you named as Monali, or why are you named as Raghava. I cannot ask, right? Similar lines, we have names given as matrix, vector, scalar, etc. And that way you also have a name called tensor. It's nothing but collection of all these numbers, etc. Okay. Just to keep that thought flowing, that there is something called as tensor. All right. So finally you get an output, right? So now let me erase this part. Suppose you take the first row. You take all of these inputs, whatever be that input. You take all these inputs, pass it through your network. Weights are randomly initialized. Do the summation part, take the value, pass it to the activation function, and finally you get an output. Final output that you get is your predicted value. Final value that you get is a predicted value. Then you compare it with the actual value here. If they both are the same, then no problem. If they both are not the same, then you'll have some loss. You'll have something called as loss. Okay, now we are getting into loss details. It's not error. It is called as loss. Okay. For the first row, it is done. Then take the second row. Take all these inputs, whatever are the inputs, pass it through your network, and then do the prediction. I mean, of course, the weights which are randomly assigned will be the same weights, and then you get the second row predicted one. Take the actual value and compare those two. If they are not the same, you get again another loss. Take the third row, take all these inputs, pass it through your network, you get an output, which is predicted value. Compare it with the actual value, calculate loss. If they are not the same, you'll have loss. In that way, you calculate loss for all the 10,000 observations. If you want to aggregate or combine all these loss values, it will be called as cost. Okay. And the function that you use, the calculation that you use for loss is called as loss function. When you aggregate, it will be called as cost function. We're not talking about error. Error is different. We'll get to it in some time. This is called as, for each observation, whatever you get is called as loss. If you aggregate means add all that or take an average of all that, it will be called as what? Cost. So when you look at this loss function or cost function, it appears like this. Say you have weight. I'm taking only one weight as an example, yes, and say you have a loss value or a cost value. Saying low batteries. So loss or cost function. You have weight. And the loss function or cost function. If your weights are randomly assigned and if the cost or loss is calculated, maybe this is a weight. This is a weight which is randomly assigned. And for that weight, this is the corresponding loss value. Now what happens is, your algorithm will back propagate, will come back. You went forward, you calculated the cost, you're coming back, right? So you're moving forward and then coming back. Moving forward to calculate the cost, coming back to update the weights is called as back propagation algorithm. Back propagation algorithm. So you're moving forward, calculating the loss of each and every observation, aggregating them and calling it as cost function. Then your algorithm is coming back to update the weights. Why do you need to update the weights? You update the weights to reduce your loss function. Now the loss is here. Again, you update the weights. And then again, you get cost. Again, you update the weights. Again, you get updated cost function. After this, if you update the weights, your cost is increasing. It has initially reduced and then it's increasing. So you stop there and you say that for these weights, I'm getting the best loss or cost. So you come back, your algorithm will come back, back propagation algorithm will come back and update the weights. And then what happens? Again, take all these observations, pass it through your network with those updated weights, do the calculation, compare it with the actual value. And again, you may have loss. Take all the loss values, aggregate them, it will be called as cost function. Take that and come back. And once again, update the weights. Again, take all of your inputs, pass it through your network with the help of updated weights. Then calculate the cost. Again, come back and update the weights. Keep doing it. And the goal is to keep updating the weights. Backpropagation algorithm's goal is to update the weights. But you're updating the weights to do what? To minimize your loss or cost function. That's the goal, right? You want to minimize it. That minimization of weight of loss or cost function is done using an algorithm called as gradient descent algorithm. Gradient descent algorithm is used to do what? It is used to minimize loss function or cost function. Backpropagation algorithm is used to do what? To update weights. So time, yeah, we have time. Sync these things into your brain. Keep syncing these things in your brain. Okay. So there are two algorithms, backprop algorithm or backpropagation algorithm will update the weights. Gradient descent will minimize the loss or cost. So of course, you update the weights to minimize this. So both of these work in tandem. Now, in gradient descent algorithm, primarily speaking, there are three algorithms. One is batch gradient descent algorithm. One is stochastic gradient descent algorithm. Another is mini batch. This is also called as SGD. It's for stochastic. Another thing is called as mini batch SGD. In all these three, you'll have two things. One is called as epoch, and another thing is called as iteration. Okay, you have something called as epoch, you have something called as iteration. Okay. In batch gradient descent, what happens is you take each and every observation, first observation, pass it through your network, get the predicted value, compare it with this actual value, you get a loss. Take the second observation, pass these inputs to your neural network, get the predicted value, compare it with this actual value, and then you get a loss for the second observation. In that way, you pass all the observations one after another, calculate the loss functions, aggregate them, you get cost function. Then go back and update the weights. Each time you update the weights, it is called as one iteration. Each time you update the weights, it is called as one iteration. What is an epoch then? Epoch is if you complete processing your entire training data one time. If you complete processing your entire training data one time, means if you pass all your observations one time through your network, it is called as one epoch. One epoch means what? If you pass all these observations once through your network, it is called as one epoch. One epoch has how many iterations? In batch gradient descent, one epoch means you take all these inputs, pass it to your network once, and you get the cost function, come back and update the weights. So only one iteration will be there in one epoch. When it comes to batch gradient descent. Then people thought, why should I wait for all the observations to go through my network, then get the cost function, and then come back and update the weights? Why should I do that? Is there no better way? Yes, there is a better way. Not better way. Are there other ways? Yes, there are other ways. And they came up with something called as stochastic gradient descent. Stochastic means random. Stochastic meaning is random. Okay. That means you randomly pick one observation, say maybe observation number 5. Randomly you pick that. You take your inputs, pass it through your network, get the predicted value of this 5th observation. Then take the actual value pertaining to that. And if they're different, you'll have some loss. Now take that loss value, come back and update the weights. Then pick randomly another input, so another observation, say observation number 1. Take all these inputs, pass it to your network, you get the predicted value. Compare it with the actual value. If they're different, you'll have a loss function, loss value. Take that loss, go back and update the weights. Take another observation, maybe observation number 987, randomly. Take the inputs, pass it to your network, calculate the predicted value, compare it with the actual value. If there is a loss, go back and update the weights. Even if there is no loss, still your algorithm will come back. Maybe it will come back and it will try to update the weights, but weights will be the same. Just remember that. Then again, randomly choose another observation, maybe observation number 100. Take all these inputs, pass through your network, get the predicted value, compare it with the actual value. If there is loss, or again, if there is loss or no loss, either way you come back, update the weights. If there is no loss, despite the updation, weights will be the same. Remember that. So either way you come back and update. So one epoch means you need to process all the observations, all these 10,000 observations at least one time through your network. So in one epoch, how many times weights are getting updated? If you have 10,000 observations, in this example, you have 10,000 observations. So how many times weights will get updated? 1,000 times. So you'll have 10,000 times. So you'll have 10,000 iterations. In one epoch, you have 10,000 iterations. Oh my God, these many times I need to update, is it? On one side, you are saying batch gradient descent, where you pass through all the observations one time, calculate the loss, aggregate, and then update the weights. On another side, you're saying each time you take an observation, pass it through, you get a loss, update the weights. These are two different extremes, right? Is there no midpoint? Then people came up with something called as mini batch SGD. In this, you need to decide one additional parameter, hyperparameter, which is batch size. It is up to you on what you define. Say you define batch size as 1,000. Right? So stochastic gradient descent 10,000 times. In this example, you have 10,000 observations. So 10,000 times it's updating the weights. Would it be time consuming? Obviously. In batch gradient descent, only one time you are coming back and updating the weights. It will be fast. Then third thing is mini batch SU. Here you define batch size. This is a hyperparameter. You need to decide something. Say it is 1,000. 1,000 means this data set which has 10,000 observations would get divided into multiple parts. Now, I wish I could just cut this part and move it here. prediction problem. There is an advanced version. Oh. And how that is. It's not coming. Anyways, that's it. So why do I want to do that? Anyways, you have 10,000 observations. One, let me 1, 2, 3, 10,000 observations. Since you mentioned that batch size equal to 1,000, 1 until 1,000 observations will become one batch. Then 1,001 until 2,000 will become batch 2. Then 2,001 until 3,000 will become batch 3. Then 3,001 until 4,000 will become batch 4. Then 4,001 until 5,000 will become batch 5. In that way, you'll have batch 6, batch 7, batch 8, batch 9, and batch 10. 5,001 until 6,000, 6,001, 7,000, 7,001 until 8,000, 8,001 until 9,000, 9,001 until 10. You have 10,000 observations, batch size is 1,000. So how many batches will we have? 10 batches. And back to our discussion that we have one epoch. One epoch means once I'll process all the observations through my network. Then in batch 1, this is what mini batch SGD, stochastic. Stochastic means random. So in batch 1, you randomly choose an observation, say observation number 2. Take all these inputs, pass it to your network, calculate the loss, keep it like that. Then randomly, maybe you chose observation number 1,000. You take all those inputs, pass it to your network, calculate the loss, keep it, store it. Then randomly you chose, say, row number 3. Take all these inputs, pass it through your network, calculate the loss, store it. Then you take randomly another observation, say observation number 999. Take all the corresponding inputs, pass it to your network, calculate the loss, store it. In this way, you process all the 1,000 observations and you get all the 1,000 loss values, loss 1, loss 2, all the 1,000 loss values, aggregate them to get a cost. Now come back and update the weights. Now the weights are updated. Keep the updated weights like that. Now go to batch 2. Randomly choose some observation. Say you chose observation number 2,000. Pass it through your network with that updated weights. I mean, from batch 1, it got updated, right? Keep the same weights. Take the inputs of 2,000, multiply with those weights, process, get the loss, store it. Then randomly choose some observation, say 1,001. Take the inputs, pass it through your network, calculate the loss, store it. Then take observation, randomly choose observations. And once all these 1,000 observations are processed, you take the cost function value, come back and update the weights. Second time you updated the weights. Then move to third batch. In this batch also randomly choose all these 1,000 observations, get the loss and then corresponding cost, come back and update the weights. Third time you updated the weights. Then go to batch 4. You choose randomly all these 1,000 observations, get the cost value, come back and update the weights. So in one epoch means all these observations should be processed once to your network. Then how many times weights are updated here? 10 times. Because you have 10 batches, 10 times it is updated. Okay. So number of iterations will be 10. Each time you update the weight, it's called as one iteration. In this way, these are the three widely used things, and people most often than not use mini batches. In mini batch, there is an additional parameter, hyperparameter, which is batch size, which has to be defined by you. Usually, this batch size is defined in terms of 2 raised to the power n, meaning 2 raised to the power 4 is how much? 16. You have 16 GB RAM, or 2 raised to the power 5, 32. We have 32 GB RAM. 2 raised to the power 6, 64. You have 64 GB RAM. 2 raised to the power 7 is 128. 128 is your RAM size, or your processors have GPUs have some GB of memory, right? Usually those are 2 raised to the power something. Hence, since you have memory or RAM or processors have values 8 GB, 4 GB in that way, it ends with something which is 2 raised to the power n. You usually choose in that way. To make use of your parallel processing, sometimes you might have a GPU and RAM, or you can have dual core rather, or quad core. Dual core means 2 cores. So your data, 2 batches will process in parallel. For that purpose, we use 2 raised to the power n as a thumb rule to come up with the batch size. Anyways, that I said. Now we are aware of what is epoch, what is iteration, what are the 3 gradient descent algorithms which are used to minimize the loss function or cost function. You're aware of the difference between loss function. Loss function is for each observation. When you aggregate it, it's called as cost function. And you're also aware of backpropagation algorithm, which is used to update the weights. Now, yes, couple of things. When you try to look at your loss function or cost function, it might look very different. And if I randomly initialize weight might come here. If it comes here, the corresponding loss would be here. And as and now I keep updating my weights and minimizing my loss, it will reach this minimum loss. And then if I update the weights further, it will increase. So your algorithm will stop here. And it says that, hey, this is the least loss or cost that I can obtain, and these should be the corresponding weights. This is called as local minimum. But then say your weights somewhere got updated here. This is the corresponding loss function. Then you update your weights, minimize the loss, update the weights, minimize the loss in that way. Keep updating the weights, keep minimizing the loss, and ultimately you get to this minimum. And then if you update the weights further, it will increase. So your algorithm stops here. Here also you have a minimum. If your weights get updated here, you end up here. So the way your weights are initialized will in some sense determine on whether you'll get stuck in this minima or this minima or this minima. This minimum loss or this minimum loss or this minimum loss. It is defined by where your weights get initialized. So each time you run your deep learning model, you can get different results. So usually you run it multiple times and figure out where you want to land, or what minima is this. Out of all these minimum values, the one which is the least among all these minimum values, the one which is the least is called as global minimum. Rest all are called as local minimas. Is there a mechanism to always reach global minima? No. If you are lucky, you'll land there. Hence, you do it for multiple times, multiple trials, multiple times you run with the hope that you might land. All you can do is, using the various techniques, ensure that you reach a better local minima. But always reaching global minima, that is where we want to be, but then it's not possible. Because the way algorithm works is that it will randomly initialize the weights. Okay, this is one thing that I wanted to tell. So the loss function or cost function is used in optimization. These are your optimization functions, wherein you want to minimize the loss function or cost. But then if you want to know how accurate your model is, how accurate my model is, if you want to know that, then what do? If your output variable is continuous, accuracy, how do you measure output variable continuous? Mean error, mean absolute error, mean absolute deviation, whatever, there are many things. Right? If your output variable is discrete in two categories, you use confusion matrix. If your output variable is discrete in more than two categories, still confusion matrix. For accuracy, if you're calculating error here, 1 minus error is accuracy anyways. But then for optimization, that is for minimizing the error or loss, if the output variable is continuous, you use same measures. Usually we use mean square error. And for output variable discrete with two categories or more than two categories, we use cross entropy, binary cross entropy or categorical cross entropy. I'll open the Excel sheet and show you this. Give me a minute. Yeah. For model accuracy, we have for model evaluation to check whether your model is good or bad. We have accuracy, error function, all these. If the output variable is continuous, you can use all these. To calculate loss or cost, you have all this. Then if you have discrete variable where your output variable has two categories, will a person resign or not? Will you claim insurance policy or not? Will you meet with accident or not? Will your flight take off or not? So on and so forth. Right here for model evaluation, we use confusion matrix or cross table or contingency table. But for optimization, we use binary cross entropy. Then if you have output variable which is discrete in more than two categories, for model evaluation accuracy, you use the same things. For optimization, we use something called as categorical cross entropy. Now, don't worry about these two, friends. We will talk about these two later, okay? Not now. I'll hide this. At least these things. Okay, fine. Okay. Now we need to understand, hey, what is this entropy, first of all? Then we need to understand what is cross entropy. And we need to understand what is binary cross entropy, what is categorical cross entropy. This is what we need to understand. This is where we stand today, as of now. Before we understand entropy, there is something called as information gain. And in the due course, I'll also talk about mean versus expected value. Once you understand these, job done, friends. Walk in the park. Okay. You might be wondering, hey, why is this guy not getting into practicals? He's just going on and on with this theory. I'm interested in practicals. But then when we get into practicals, my dear friends, when I say that activation function is ReLU, activation function is damage, you're creating a dense function, right? You're using a loss function as categorical cross entropy. Optimizer is some add-on. You should not be confused. So once we understand all this theory, like batch size we understand now, epochs you understand now, you understand what do you mean by validation data. So you understand all these, once you understand all these aspects, right, when I put it in code, you'll not be confused. You'll not be taken aback. Oh my God, what is this new term, right? So I'm explaining all the theory. Once all the theory is done, we will do it practically using the Python program. Once we do it, all these options will be there and you should not be taken aback. You should not be confused. That is the reason why we are trying to understand theory first. And once we crack this, we'll get into practicals. So, time to take break. So let us now talk about information gain, entropy, and cross entropy. For this, add open sheet. This makes sense. I'll just explain the math and then we'll get into the other discussions. If someone says sun rose in east, sun rises in the east. Today sun rose in east. For this statement, what is the information in this? Is this giving you any good information? If this information gets scrolled at the bottom of a news channel on the screen, that today sun rose in the east, what information will you have in this? Is that a news? Is that a new thing? Absolutely no. Right? So there'll be zero information in this, very low information, absolutely nothing. Everyone know that sun rises in the east. And what is the corresponding probability? What is the probability that sun rises in the east? High, very high in fact. And then say there is another statement which says, there was an earthquake in Hyderabad, India. And if this news appears on a news channel, would you have information in this? Very high information. And what is the probability that there will be earthquake in Hyderabad? Very low. Now, when you look at this information and probability, you will get a feel that, you know what? Information contained in any event, like sun rose in the east or earthquake in Hyderabad, is inversely proportional to the probability of event occurring. There is inverse proportional relationship. If the probability is high, information is low. If the probability is low, information is high. So there is inversely proportional relationship which exists. This can also be written as inversely proportional minus probability of this event. And usually we take log for ease of calculation. Probability of event. Log is taken only for ease of calculation. That's it, nothing else. Usually when you have big numbers, taking log will reduce that. That will ease your calculation. That's the only purpose that we take log. Okay. So information is log of this. This is the information gain only. Now, I'll take a slight detour and explain you about mean. What is mean? You add all the values and divide it by the total count. This is called as mean. If you invest in a government bond, or if you get a provident fund interest rate on that, PF, or if you invest in some government bond, more or less the return that you get will be fixed. That means if you invest 100 rupees, if government says that I'll give 8% interest, then they'll give you 108 rupees. Or if you have $100, if government says that I'll give you 8% if you invest this in some government bonds, that means you get 108 rupees total. $8, $108. This is certain. You will get for sure. But then if you go and invest in other company stocks, such as Microsoft or Google, or if you invest in any other stocks, what would happen? Will you get the same money every time? No. If you invest $100, sometimes you might get $110, sometimes you might get into losses of $90, etc. So the output, the return that you're going to expect varies. That means there is some probability associated. The moment output varies, there is some probability. There's 10% probability that you might get $10 extra. There is 1% probability that you might lose $5, so on and so forth. That whenever you have probabilities, this mean will be called as expected value. And the formula is summation of I equal to 1 until n xi into probability of xi. Xi into probability of xi. When do you use this formula? When you have uncertain output, when you have probability which gets involved. When the output is not certain, when you know for a fact that output varies, we'll have something called as expected value. Probability formula is number of interested events divided by total number of events, which is n, total number of events. This is a probability formula. Okay, so simply put, in this same formula, if you just multiply it with probability of xi and remove n, that's good enough. This would be called as expected value. If you just multiply by probability value and remove this n. Why are removing n? Because in probability anyways that n is there. Okay, so if you're not understanding this part, absolutely fine. I completely am with you. Just remember one thing, that when the output is certain, then this is the right formula. When your output is uncertain, if it varies, then you use expected value formula. Why are you talking about these things? Hold on. So I'll apply the same logic to this information. Now what we will do is, this is the information gain formula, that is information containing an event is proportional to minus log of probability of this event. Why minus? Because probability you brought it on the top. Why log? Because for ease of math calculation. This is called as information gain. Now, if there is probability that you get into picture, like this expected value, if you bring in probability into picture, it is called as nothing but entropy. Entropy is also called as loss. Okay, and the formula will be exactly like this: summation of I equal to 1 until n xi is this into probability. So, and you also have minus sign, so I'll put minus sign. Now first we'll put this probability value, probability into log of probability of log of probability into probability. Exact same formula, friends. We are not doing any change. This x is nothing but this one. Probability and investment probability. This is called as entropy formula. Okay, simple. Next. If this is entropy formula, then what is cross entropy? Is something that we need to understand. First of all, let me use this formula and help you do some calculation. Okay, this formula help you do some calculation. Entropy is nothing but loss. Already we spoke about loss function. Entropy is a loss function. Now what I'll do is I'll get to this. Yeah. So this is a formula of entropy. So I'll not talk about all these things. I'll just talk about entropy. Let's calculate this for a variable called ball size. Okay, I'll take this input called ball size. This is a data set, small data set for a calculation purpose, where output variable is whether the football will be useful for playing or not. And in this you have ball size, ball color, and price. These three are three inputs. Given these three inputs, you need to classify whether the ball is useful for play or not. If it is useful for play, why? Yes. If it's not useful for play, n. N means no. Now say I take ball size just to show you how this entropy is calculated. And you come up with, say, a rule, which is you have all these numbers, right? Usually what decision tree does is, okay, come on. Okay, I'll not be digressing from the main point. Okay. So it creates some rule. For example, ball size less than or equal to 50 and ball size greater than 50. Say your algorithm came up with this rule classification. This rule that you have come up with, less than or equal to 50 means, say, you're saying it will be useful for play. Greater than 50 means it will not be useful for play. Now let's take the first observation. In the first observation, you have 10. Is 10 greater than 50? No. Is it less than or equal to 50? Yes. If it is less than or equal to 50, what will be a predicted value? It will be yes. And what does your actual value say? Actual value also says yes. Wow, this is a right prediction. Let's go to the second observation. You have 1. Is 1 greater than 50? No. Is it less than or 50? Yes, it's less than or equal to 50. If it is less than or equal to 50, will it be useful for play? Predicted value says yes. Predicted and actual. And what does your actual value say? Yes. Go to the third observation. You take 50. Is 50 greater than 50? No. Is it less than or equal to 50? Yeah, it is equal to 50. So the predicted value says yes. What does your actual value say? Yes. Right predictions throughout. Let's go to the fourth observation. It is 100. Is 100 less than or equal to 50? No. Is it greater than 50? Yeah, 100 is greater than 50. So predicted value says no. But what does your actual value say? No. Is this right prediction? Yes. Let's go to the fifth observation. You have 1000. Is 1000 less than or equal to 50? No. Is it greater than 50? Yes. What does the prediction say? No, won't be useful for 50. What does your actual value say? No. Good. Now, if you want to calculate entropy, this is how you do it. This is left-hand side. This is right-hand side. Since you have throughout the right predictions, what should be the loss? Anyone? What should be the loss? Loss should be 0. There should not be any loss. Right? There should not be any loss. Why? Because all are right predictions, right classifications. Now, if you want to calculate entropy, you need to calculate entropy for the left side as well as entropy for the right side. First, let us calculate entropy towards the left side. And entropy formula is very well given here, that it is minus summation of I equal to 1 until, you have two classes, yes and no. So I equal to 1 until 2 probability value into log of probability value. This can be expanded as I equal to 1 if you put minus sign instead. P1 into log of P1 is 2 minus, when you substitute I equal to 2, it becomes P2 into log of P2 is 2. If you look at the right side, it is less than or equal to 50. So you have 3 observations. And P1 is yes, P2 is no, you have 2. P1 equal to yes and P2 equal to no. On this, what is the probability? How many yes do you have? 3. Out of 3, 3 out of 3 are yes. So you get 1. How many no you have in this? How many no do you have? There is no no. 0 out of 3 are no. So you get 0. If you say calculate it, P1 is 1. So minus 1 into log of 1 minus P2 is 0. 0 into log of 0. Log of 1 is 0, friends. 0 into anything is 0. Minus 0 into anything is 0. So you get 0. So entropy towards the left side will be 0. Obviously, all 3 are right predictions here. You should get 0 only. Then let's look at the right hand side. Right hand side is what? Greater than 50. Greater than 50 means these two. P1 is yes. How many yes do you have in this? 0. 0 out of 2. There are 2. There are no. So 0. How many no do you have? 2. Out of 2 entries. So you get 1. When you solve it, it becomes minus 0 into log of 0 base 2 minus P2 is 1. 1 into log of 1 base 2. Log 1 is 0. 0 into this is 0. 0 into anything is 0. So you get 0. So entropy towards the right is also 0. Right? So overall entropy is 0. That is what we wanted, right? Entropy, is it going to be some value or 0? Because you have all the predictions which are correct. Loss should be 0. That is what we got. Both sides are 0. This is how you calculate entropy. Now, this is not what we are interested in. We are interested in cross entropy. Why are we interested in cross entropy? Because cross entropy is something which is used as a loss function or cost function in your deep learning. So how is it calculated? Let me tell you. Suppose you have images, example of images, and you have, say, tiger, lion, cat, and dog. Images. And you have the actual data, which is called as P. And you have P is called as actual data. So actually say you have an image of tiger. Obviously, you'll put a 1 here. That means there's 100% probability that it is a tiger. Actual data will have the correct label only, right? It will have the correct name. So this image is tiger. So obviously you say this is tiger. This is not lion, not cat, not dog. It's tiger. 100% probability that it is tiger because it's actual data. Then say you build a model and you're supplying your new image to your algorithm. And then you get the predicted values. In the predicted value, it might say there is 70% probability that it might be a tiger. There might be, 10% probability that it could be a lion. Maybe there's 15% probability that it's a cat. Maybe there is 5% probability that it's a dog. Now, if you want to calculate cross entropy, the formula is exactly the same. Minus summation of I equal to 1 until n pi into log of qi. That's it. That is the only difference. Now here you have 4 classes. 1, 2, 3, 4. Tiger, lion, cat, dog. 4 classes. So you put it as minus summation of I equal to 1 until 4 pi into log of qi base 2. Keep substituting values in this. So what would happen is eventually, let me put it here, minus p1 into log of q1 minus p2 because I equal to 2 now into log of q2. I equal to 3 when you put, you get p3 into log of q3 base 2. So when you substitute I equal to 4, you get p4 into log of q4. P1 is 1, so minus 1 into log of 0.7 minus P2 is 0, 0 into log of 0.1 minus 0 into, that is P3, log of Q3 is 0.05. minus 0 into, which is P4, log of 0.05. 0 into anything is 0. 0 into anything is 0. 0 into anything is 0. When you solve this, you get some number. That is your cross entropy value, which is nothing but loss function or cost function. And this is what your model should minimize. In deep learning, that is what we discussed, right? So this is something that has to be minimized. And if you have only cat and a dog, for example, or tiger lion, only two classes, then it is called as binary cross entropy. Same formula. The only difference is instead of n equal to 4, you'll have n equal to 2 for binary. Categorical means when you have more than two categories. Here you have 4 categories. So your loss function would be categorical cross entropy. All with me? Okay. This we had to understand to proceed further. All this is fine. This is a typical human brain. This is how it looks like. You have dendrites like connections. Dendrites are like connections, right? And you have the cell body, and more on like that. And then you have the output. Same, I mean, I would not spend a lot of time on this because this is a typical neuron in a human brain. This is not a biology class, but yep, you can spend some time, understand what means what, right? And how it is correlated to artificial neural network. Okay. Way back, people first came up with an algorithm called as Perceptron algorithm, way back, in which you'll only have input layer and one output layer. That's it. And only one neuron in your output layer. No hidden layers. One neuron in your output is called as Perceptron algorithm. And to move forward, calculate the loss and come back and update the weights, people have first come up with something called as Hebbian learning. Some formula to update the weights. Weight plus your input into the output variable, that will give you weight. And the bias is equal to bias plus input into output would give you new bias. This is how they came up with. Then came Windroff-Hoff learning rule, a different way of updating the weights. And this is something which became famous. And that is what we will focus upon. Okay. So we have Perceptron algorithm, which was actually introduced to the world by a scientist called as Rosenblatt. And we are going to strictly use this formula to update the weights and see. We'll take a very toy example and solve it. New weights is equal to old weights new weights is equal to old weights plus eta value, which is nothing but learning rate. And the eta value ranges from 0 to 1 into the error, which is actual value minus predicted value into the corresponding input. We'll understand this using the formula. But here there is this new thing called as learning rate which got introduced, right? I'll explain briefly about that. So you have some loss function in that way. If your weights are here, updated here, randomly assigned here, say your weights are randomly assigned here, then if you give a eta value, which is very close to zero, very small eta value when you give for learning rate, to take huge amount of time to get updated to reach the minimum. Most often than not, you might get tired and say, hey, let me stop this algorithm. It's running for 2 days now. So you might not reach the minimum if you give a very small learning rate, because it will take huge number of iterations to update the weights. Maybe you'll tell your algorithm that run 1,000 iterations. In 1,000 iterations, maybe it will reach only here. You missed out opportunity to reach there. But if you give a very high learning rate or eta value, what happens is you take big steps. One update directly comes here. Second update will go there, right? Or even worse, the update might go here. Then the update might go here. Then it might go here. You might not even reach your minimum. Right? You might not even reach your minima if you give an eta value which is very high. Usually eta values are neither very small nor they are very high. But I should tell you that eta values are usually started using a small value like 0.01, 0.001, but not smaller than this. If you give smaller than this, it will take huge amount of time to reach the minimum. If you give eta value as 0.1, 0.2, 0.3, it will keep jumping like that. It will not be able to reach the minimum. Okay. Now, let us get into this discussion. Perceptron algorithm. Say you have 4 inputs in the data set. I'll put down the data set here for everyone's benefit. In this toy example, you have 4 points and you have an output variable and input variables. Okay, and you have only 4 points. 1, 2, 3, 4. First one is z equal to 0. Okay, and the inputs pertaining to that are -1 and 1. -1 and it should be -1, right? So -1 and -1. Then second value here is z equal to again 0. Inputs are -1 and 1 by 2 is 0.5. -1 and 1. Then third is z equal to 1. We have 1 by 2 and 1 as inputs. 1 by 2 because it's 0.5 and 1 here. Next, this is also z equal to 1, then 1 and 1 by 2. This is the data set that we have. Then, when the algorithm is first run, inputs are, say, randomly chosen. So randomly, if you have 2 inputs, you'll have 2 weights. Weights are randomly chosen as 0 and 1. Say eta value learning rate, you have selected as 1 by 3. Random, this eta rate or learning rate is also called as hyperparameter. So eta value. Formula is new weights is equal to old weights plus eta value into actual value minus predicted value into input. Now, if you look at this classifier, this has given this classifier. Anything which falls above is z equal to 1. So for these two, it's right prediction. Anything which falls below is z equal to 0. This is also right. But this has been misclassified. It is actually z equal to 0, but since it's falling above the line, it will be predicted as z equal to 1. So for this, weights have to be updated. Loss is there, right? This is called as loss. Incorrect prediction. So you need to update the weights. How do you update it? New weights equal to old weight. So old weight, take the old weight 0 plus eta value, which is 1 by 3. Actual value minus predicted value. Actually, it is 0. Z equal to 0. But since it's above this line, it will be predicted as 1. So 0 minus 1 will be minus 1. So you have that minus 1. Into what is the first input? If you look at this, it is minus 1 comma 0.5, which is 1 by 3. So minus 1. You multiply it with that input, you get 1 by 3. And you also need to update the other input. So new weight is equal to old weight, which is now 1 into eta value is 1 by 3 into actual minus predicted is minus 1 into 0.5 is 1. When you solve it, you get 5 by 6. So these are the new set of weights. You have 1 by 3 and 5 by 6. These are the new set of weights. Now that you updated the weights, the classifier adjusted itself a bit. And now it's like this. But still, this has been misclassified. Above is z equal to 1. Below is z equal to 0. This is z equal to 0. But since it's above the line, it will be classified as z equal to 1. So you need to update the weights. New weights equal to old weight, which is 1 by 3, into eta value 0 minus 1, which is actual value minus predicted value. 0 minus 1. This is actually 0. Since it's above the line, it will be classified as 1. 0 minus 1 is minus 1. Into the input. One input is minus 1. Another input is here. 1 by 2. 0.5 or 1. Into minus 1, you get this. That's a new weight. Now, other weight also has to be updated. So, formula is new weight equal to old weight 5 by 6 plus eta value, which is 1 by 3, into error, which is actual value into minus predicted value. Actually, this is 0. This has been predicted as 1. So, 0 minus 1 is minus 1 into the input, which is 1 by 2. When you solve, you get this. These are the new weights. Now, with these new weights, once again, when you plot, you get the right classifier, wherein you have no loss. Everything is correctly classified. So the points which fall above the line are z equal to 1, and actually they are z equal to 1. The points which fall below are z equal to 0. They are actually z equal to 0. So job done. This is the right prediction. Okay, but the challenge with respect to this perceptron algorithm is something else we'll talk. But then look at this. Every neuron will have two components, integration component and activation component. Usually the integration component is summation. And the activation component, within activation component, you'll have activation functions. These vary. We'll talk about that. But then, perceptron algorithm only handles linear patterns. For example, if you have data like this, then it can draw a line and easily it can classify these two. Pink class, blue class. Easily it can classify. Because there is a linear boundary. However, you might also have nonlinear boundary like this. In these kind of scenarios, it is not easy to segregate these two, pink class from blue class. It is not easy. So how would you segregate? Using a single line, you cannot. If you have multiple lines, maybe you can. For example, 1, 2, maybe 3, maybe 4. If you have multiple lines, then you can segregate the pink class from the blue class. If you have a single line, it can handle a linear problem, and it's Perceptron. Perceptron algorithm can do it. Multiple lines, multiple perceptrons. Hence, you can call this as multi-layered perceptron because you have multiple lines. Perceptron can handle only linear boundaries. Non-linear patterns can be addressed using multi-layered perceptron or by changing your integration function. Remember, every neuron will have integration component and activation. Integration usually is summation, but you can change that and make your algorithm handle non-linear patterns. What are those non-linear patterns? You can have a quadratic function. Quadratic function, I mean, normally if you have summation, what would you write? Function is equal to summation of I equal to 1 until n wi xi plus your b value, or b plus w1 x1 plus w2 x2 plus w3 x3 in that way. But when it comes to, this is a simple summation if you use this. If you use quadratic function, the same thing would be written as b plus w1 x1 square plus w2 x2 square plus w3 x3 square in that. There is also a spherical function which can handle spherical boundaries. Okay, and here you write x minus w whole square. So this basically changes as b plus w1 minus x1 whole square plus w2 minus x2 whole square, or x2 minus w2, either way it will be the same. So on and so forth. Why take all that headache? How many will you try out? Simply, rather than changing your integration function, proceed further with multi-layered perceptron, job done. Okay, so I'll stop here. And in the next module, we will discuss about multi-layered perceptron, and we'll discuss about deep learning practical issues, regularization techniques. A lot of optimizers are there still. Adam, Adagrad, Adadelta, all those things we'll talk. And then we'll get into the practical stuff. I thought in this module, I could get to the practical stuff of running the TensorFlow and Keras module code and PyTorch, but I could not. So in the next module, we'll do that. However, whatever you have learned, it is very easy to forget. Okay, it is very, very easy to forget if you are not in touch with the subject. So go to our website, click on mind map. There'll be a drop down called all. Do a drop down on that. You'll have something called as AI and deep learning. Click on that. Click. And please read this. Okay. A lot of things have been listed here. You at least at a bare minimum go to deep learning primer. Look at all these things: compositionality, initial hidden layers capture low-level features. Next, hidden layer captures high-level, mid-level, high-level features. Then neuron has two components: integration function and activation functions. Right. So please at least at a high level go through these. All the deep learning, challenges and practical issues, we will talk about it in the next module for sure. Just go through these, read it, get yourself accustomed to it. All right. If you read this mind map on a daily basis, you will clear interviews. So don't worry. Just focus on this. All right. Thank you all so much for your patience. and we will certainly connect on in the next module and take it forward. But before that, one more thing I need to talk about. So friends, I aim to conduct sessions on emerging technologies. Okay, and from 6th onwards, from 6:30 p.m. onwards, you will have machine learning on cloud. Okay, which will be from, or let me say it will be from 7 to 8 without disturbing anything. So it'll be from 7 to 8, machine learning on cloud. Please attend and understand what are the emerging trends, right? So I shared the link here. If you feel you're going to forget about different things that are going to happen here, just click on subscribe and this notification. You'll receive emails directly from YouTube. There we go. I request you all to please do that. And I strongly recommend you guys to go to the Python programming here for 20 hours. I have delivered the sessions, so you might want to go through this, right? It's up to you. All right, friends. Thank you. We'll meet in the next module and take this discussion forward.